Hey, welcome back, guys. Today we're going to talk about something that's a little different. We're not going to be talking about Arduinos or robotics. Instead, I'm going to be showing you how to count. I know you might be thinking that's silly. You're in middle school, you know how to count, right? And I'm sure you know, we start at 0, and then we go 1, 2, 3, 4, 5, all the way through 9. I'm sure you've done that before, but we kind of have a problem that we just kind of automatically know because you've probably memorized it through grade school and such, that in order to get to the next number, something strange actually happens. We have to create a new place value and start recycling our numbers, basically. So we all know this place right here. When there's only one digit, that's the ones place. And we know that at the next number, the ones place starts over at 0. And we create next to that a new place. And that would be 1. So we just say that we have basically one group of 10 and 0 groups of 1 now. I'm sure we've all seen and known that. And this works really well for us as human beings. But today we're going to learn to count in a way that solves a problem that's been very important for our everything in the last 50 years or so. And that is, how does something like this count? This is an old computer processor. And computer processors, well, they're kind of different. Computer processors are basically switches. They can only understand two things, as all switches can only understand. They can understand off, they can understand on. So our goal today is to understand, how does every computer or everything with computer processor in it, and that's computers, laptops, Chromebooks, cell phones, almost every TV now has a processor in it. Your game consoles, your cars, the world around us is surrounded by processors. And processors, even though you might think they're pretty sophisticated and they can do lots of neat things, they're really pretty simple because they can only understand two things. They can understand off and on. So we're going to explore the world of processors and how they count by kind of building on what we already know about counting. So let's go ahead and just look at the numbers that we already know and love and use every day in our math class. There are 10 digits here. Now, a lot of people might say, well, I only see the number 9, but don't forget about our buddy 0 here, right? So if we take 1 through 9 and add 0, that gives us 10 digits. For those of you who are real sharp with language arts and those kinds of things, you probably know that the root word for 10 is dec. And when we're talking about the name of the numbers that we use, the 10 numbers that we use all the time, that's the decimal number system. And we call it decimal because there are 10 numbers. Well, as we already kind of said, our computer processor, it cannot ever understand 10 numbers. It only understands offs and ons. That's 2 possibilities. You can see with the decimal number system, we have 10 possibilities, and we can rearrange these 10 possibilities lots of different ways. We could make the number, 3, or I could make the number 75, right? So these possibilities kind of get mixed up to make lots of different things. So we're going to see how we have to do that for computers. So if I take and rewrite my decimal numbers here, we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll go to 10 here. We need to think, how do computers count? Well, if they can only understand 2 things, off and on, that means they really only understand 2 numbers. Again, for those of you who have a really strong background in language arts and words, start thinking to yourself, what's the root word for two? Well, I rode to work today on a thing with two wheels that you pedal, like a bicycle. A lot of old airplanes had two sets of wings. Those were called biplanes. By now, I hope you figured out that the root word for two is bi. So the kind of numbers that we're going to talk about are binary numbers. And they work exactly like the numbers that we use every day, except there's a lot fewer of them. So just like our number system, the decimal number system, computers start off with 0 when there's nothing. And if you think about a computer that only stands off and on, that 0 is going to represent off. Right. And then they go to the next number, which is a 1. And that represents on. But we have now, if you're a computer, run out of digits. There are no more things you can understand. So in binary, we can't go and make the number 2 like that. That does not exist in binary. Instead, we have to kind of go back and look at our decimal numbers and think about what happens when we run out of digits in our own decimal numbers. You could see we have a bunch of one-digit numbers from 0 all the way to 9 here. But then at 9, I run out of digits. So just like we do in the decimal number system, where we recycle the digits in the ones place and we add a new place value in the tens place, we have to do the same kind of thing in binary. So the number 2 in binary, well, that's pretty simple. We ran out of digits, so we know that the ones place has to turn into a 0. And then the place next door to it has to increase. And the only thing I can increase to in binary is 1. So in binary, what looks like our number 10 is really the number 2. I probably won't ever say 10. I'll call this 10. So in binary, 10 is the same as our decimal number 2. And this is a good spot for me to kind of hop over here and maybe make you a little bit angry at all the math teachers that you ever had in your life. Because when you were in grade school, you probably had to memorize hundreds of addition facts. Well, binary is a lot more simple. Binary only has 4 addition facts that you need to memorize. And a lot of them, 3 of them at least, are super simple to get. So the very first binary math fact is 0 plus 0. That's nothing combined with nothing. Well, if I have nothing in one hand and nothing in the other hand and I put it together, I still have nothing. So 0 plus 0 still equals 0. So in binary, if I ever have to go 0 plus 0, well, I still have 0. The other math fact is 0 plus 1. Well, if I have one thing in one hand and nothing in the other, when I put my 2 hands together, I now have one thing. So that's still 0 plus 1, just like you're used to. That's still 1. I can also have, and this might seem a little silly, but it is technically a little different, 1 plus 0. This time, that one thing just changed hands. So when I put 1 plus nothing together, I still get 1. And then this is the one that kind of trips people up from time to time. 1 plus 1. Now remember, these are the binary math facts, not the decimal math facts. Normally I would say 1 plus 1 is 2, but our computers don't understand 2. So I'm not going to keep this 2. I'm going to look and see what we've already done. Oh yeah, we know what 2 is in binary. We know that 2 is 10. So that's my 4th addition fact, is that 1 plus 1 equals 10. Okay, and the reason I mention this is because we are going to count up in binary, and just like normal counting, right, like to get from 1 to 2 in decimal, I have to go plus 1, right? Every time I count up, I go plus 1. We're going to do the same thing in binary just to see what counting in binary is like. So we have 0 and 1 and 2 in binary. So to get to 3, I have to go, and I'll just do that work down here, 1, 0, plus 1. That's how I get to the number 3, because there's the number 2, plus 1 for counting. Well, let's use our math facts here to help us out. This works just like every other addition you've ever done in your life. We go 0 plus 1. Well, I'm going to find that up here. Oh, there it is, 0 plus 1. That's 1. And then 1, and there's nothing below the 1, so that's really a 0 below it. So it's 1 plus nothing. Well, that's still 1. So the number 3 in binary is 1, 1. Okay, well, let's think about how to get to the number 4 in binary. Well, the number 3 is 1, 1, and I'm going to count up by 1, plus 1. Okay, I'm going to use my math facts to help me out here. So I can see that 1 plus 1, oh yeah, that's right there. Well, this is interesting. 1, 0, what do I do now? Well, just like you've always done, if you have two numbers and they create a two-digit number when you add them together, like 1 plus 1 equals 1, 0, just like if I were to go 8 plus, let's say 18 plus 8, right? I would go 8 plus 8 is 16. I would normally write the 6 and carry the 1, and then I would add the 1s together. Remember, this is a decimal problem. 1 plus 1 is 2, so 26. So if I ever create, like this 6 right here is really 16, if I ever created a two-digit number, I have to carry the other digit over. Well, the same thing happens here in binary, but I think it's even easier here in binary. Let me show you. So 1 plus 1 we know is 1, 0. So I write down the 0, and I carry the 1. And then I get 1 plus 1 again. Well, we know that's 1, 0, so I write down the 0, and I carry the 1, but there's nothing to carry it to, so it really drops down. So the number 4 in binary is 1, 0, 0. All right, now let's move on to the number 5. So 1, 0, 0 plus 1, because 1, 0, 0 is 4. Well, this one's pretty easy. I just go 0 plus 1, that's 1. The 0 drops down, the 1 drops down. So the number 5 in binary is 1, 0, 1. And let's get the number 6 in binary. So I'll write 5, which is 1, 0, 1. Plus 1 to make 6. Well, here again, I have 1 plus 1. And if you remember, I'm going to write the 0, carry the 1, and I get 1 plus 0, which is 1. And this 1 drops down. So the number 6 in binary is 1, 1, 0. And we'll write the number 6 in binary down, which is 1, 1, 0. And then to get to number 7, I go plus 1. 0 plus 1 is 1. 1 plus nothing is 1. 1 plus nothing is 1. So the number 7 in binary is 1, 1, 1. Ooh, some of you savvy watchers out there might have recognized, like, oh, every one of those place values is out of digits now. I bet that's something like 999, and you'd be right, and let's see why. So if I go 1, 1, 1 for 7, plus 1 for my count, I'm going to use my math facts to help me out again. So I get 1 plus 1. Well, we know 1 plus 1 is 1, 0, so I'm going to write the 0, carry the 1. 1 plus 1, that's 1, 0. I'm going to write the 0, carry the 1. I get 1 plus 1. Again, 1 plus 1 is 1, 0. I write the 0, I carry the 1, there's nothing for it to carry to, and I drop it down. So the number 8 has a brand new place value, 1, 0, 0, 0. And I just kind of know this. I just really wanted to get to 8 to show you that last math problem. 9 just increases by 1, so it's 1, 0, 0, 1. The number 10 is 1, 0, 1, 0. And that's kind of where we're going to finish our chart. Now, a couple things I want to point out. If I look at all the decimal numbers, and let's look at the even decimal numbers like 2 and 4 and 6 and 8 and 10. If I look at their binary equivalents, I can see that in binary, all the even numbers end in 0, like 1, 0, 1, 0, 0, 1, 1, 0. So that's one thing I want to point out, is if you think that you've converted a number from decimal to binary, pay attention to, if I'm converting an even number, it should end in 0. If I'm converting an odd number, it should end in 1. Right? So all the odds end in 1, all the evens end in 0. One other thing I kind of want to point out to you is, let's look at all the places where we created a new place value. Right? Like I created a new place value at 2. I created a new place value at 4. I created a new place value at 8. And you can see every time I create a new place value, the decimal number where I created it, well, that kind of doubles, like 2 to 4 to 8. The next one's probably going to be 16. And that's going to be an important thing. Let's go ahead and kind of look at that too. So in binary, we can do a lot of binary calculations pretty quickly just by understanding place values. So just like every other number system, we have that very first place value is the ones place. And except this one is not the tens place because I don't have 10 different numbers, or 10 different digits, excuse me. I have only 2 digits, so this has to be the twos place. And, right, every time, like we pointed out over here, it doubles. So if I double 2, that becomes 4. If I double 4, that becomes 8. If I double 8, that becomes 16. So how can we use these place values to help us out a little bit? Well, here's how we can use it to help us out. Let's say I had a binary number, okay? Let's say I had 1, 0, 1, 1, 0. Well, just looking at that binary number, 1, 0, 1, 1, 0, I can already tell you it's going to be even because it ends in a 0. But let's look and see what this is telling us. Just like what you know about decimal, this is telling us how many groups of certain things we have. Like this is telling me I have one group of 16, so I would write down 16, plus 0 groups of 8. Well, that means I don't have anything there, so I'll just write down a 0. Plus 1 group of 4, so I'd write down a 4 because I do have a group of 4. Plus 1 group of 2, so I would write down a 2. Plus 0 groups of 1, so I would write down plus 0, right? Because that's telling me I have nothing. So this is really 16 plus 0 plus 4 plus 2 plus 0. Or, if you want to take a shortcut, you can even say ignore the ones with the zeros on it. So this is really 16 plus 4 plus 2. Well, if I add all those things together, 16 plus 4 is 20, plus 2 is 22. So this number, 10110, that's the number 22 in binary. So I could use those place values like that to help me out. And if you wanted, you could keep adding place values. The next one would be 32. The one after that would be 64, then 128, then 256, 512, 1024, and it goes on just doubling all the way for forever, right? So if you want to see just one more, I can kind of go like this. I can go 1, 0, 0, 0, 1. So I'm thinking about it. All right, so this tells me I have 16, no 8s, so I'm going to ignore that. No 4s, I'm going to ignore that. No 2s, I'm going to ignore that. And 1, 1, so I'll just write down 1. So 16 plus 1 is 17. So the number 1, 0, 0, 0, 1 in binary is 17. We can also kind of go backwards from that, right? I can give a decimal number and figure out what its binary equivalent is. All right? So let's say I had the number, let's say I had the number 28. Well, what would that be in binary? Well, I've really just got to look at my place values and think which place values am I going to use to create 28. Well, obviously 16 fits in there. So I'll go 16, and then I'll go plus. Would I use an 8? 16 plus 8 is 24. So yep, that gets me pretty close. I'd put an 8 in there. So 16 plus 8 is 24. I have to go 4 more. Oh, so I only need 4 more to get up to 28, so I'd use the 4. And that puts me at 28. 16 plus 8 plus 4 is 28. So I don't need a 2. So I'll put a 0 there because I'm not going to use any 2's. There are no 2's in that number. And I'm not going to use any 1's because I'm already at 28. So I'll put 0 1's. So in binary, the number 28 is 1 1 1 0 0. All right, I'll show you one more here to get you on your way. Let's say I wanted to have the number 25. What will that be in binary? Well, you might want to pause the video right here and see if you can figure that out on your own. I'll join you in just a second. Welcome back. I hope you got it. So again, I'm going to look at the numbers that I have and see what do I need to add together to create 25. Well, obviously I'm going to use 16, so I'll put a 1 there. So 16 plus, well, am I going to include the 8? 16 plus 8 is 24. So yeah, I do need that 8. So I'll put an 8. Am I going to use the 4? No, the 4 would be too big. That would get me at 28. So I'll put a 0 there. Am I going to use the 2? No, that would put me at 26. So I'll put a 0 there. Am I going to use the 1? That's plus 1. Yeah, that would put me right at 25. So I'll put a 1 there. So the decimal number 25 in binary is 11001. And that's a real quick introduction on how to count in binary, how to change a binary number to decimal, and how to change a decimal number into binary. Thanks for watching, and I hope you have a great day.